I'm Manu Sridharan. I'm going to talk to you about some exciting work we're doing around program analysis at Uber. So let me start at the highest level. So what is Uber? And actually, I don't think I even really understood how much code, particularly in the mobile applications, was present until I started. So Uber is multiple apps. We have a rider app. This is probably the app you're most familiar with for booking a ride to go somewhere. And then we have a separate app, the driver app, where drivers can, see who's requesting rides and get navigation directions. And then there's more and more apps that are coming, like Uber Eats for ordering food. And there's more planned for the future. And beyond the number of apps here, we have separate apps on both iOS and Android. So you can see how this is adding up to a lot of mobile application code. So what's interesting about mobile application development, particularly at Uber? Well, one thing that I found very interesting is that Uber cares a lot about reliability. And so everyone should care about reliability. Uber really cares because it's business critical, right? So if the rider app is crashing, then someone's potentially stuck, right? And they can't get home. Maybe they end up using some other competitor's app. If the driver app is crashing, a driver can't earn, right? Directly infects their income. Another interesting point is that using Uber apps almost always involves a payment, right? So when the customer's actual money is involved, there's potentially a higher expectation that things work correctly, and then there's a big customer service burden when things aren't working correctly. And finally, at least by modern standards, apps can take a significant time to patch, right? So if you've got some problem in server-side code, once you diagnose it, you can switch over users to the new code, basically instantly. But with an app, when you have app review processes and you have delays in people actually installing the new app, it can be, on the order of weeks or even for months. You can still see crashers from old versions of the app in your logs. So very important that the mobile app code is reliable. And in fact, this is the mission statement for Uber. And you can see that reliability is a big part even of the mission statement of Uber. It's a big deal. So at the same time, Uber needs to move fast. So we're constantly developing new features in these apps for new functionality, and also different parts of the world need different features. So we have hundreds of developers working on the mobile applications simultaneously. This leads to on the order of hundreds of commits per day. And I did measure, and we do have millions of lines of code for our mobile apps. And one of the explicit goals in Uber engineering is to let builders build, right? So whatever tooling we develop, we don't want it to get in the way of developers mostly being able to get done what they need to get done. And also, it's an explicit goal, when you have this many developers, you really want them to be able to work independently and not be constantly stepping on each other's toes. So this is, to me, kind of the key interesting question in trying to bring more program analysis to Uber, right? Is how can Uber both move fast and keep reliability high, right? And I don't think I have the answer yet, but one thing that I think is exciting that we've been exploring is this idea of modularity, both in design of the apps and in the analyses we design, and how can these interact, right? So I'm going to describe how some of the app design principles that are already in effect at Uber emphasize modularity, again, so that developers can work on their features independently, and that they can also, and that helps them to move fast by not stepping on each other's toes. I think there's a lot of potential for program analysis to both enforce the modularity in these designs and also leverage it, right? So if you've got independent modules, hopefully we can do analyses of these modules independently, scale better, and also get more precise results, basically by avoiding pollution in our analysis results from completely unrelated code. And one other cool thing is that in working with a lot of the core platform engineers, there's a very strong willingness at Uber moving forward to adjust the design of these apps in order to aid analysis if it's going to really help reliability, performance, or something else that we care about, which I find very exciting. A lot of my background in program analysis, basically the idea was you've got this huge code base and analyze it, but that's it. Whatever crazy stuff it's doing, you make your analysis do a good job with it. And so the ability to sort of influence the code as it's being written to make analysis easier, to me, is just very refreshing and very exciting. So in the rest of this talk, I'm going to briefly cover a few topics. First, I'm going to give a little bit more detail on this idea of designing for modularity and analyzability. Then I'm going to go through a case study of nullness checking, which is analysis that was already being used at Uber and which we've managed to improve significantly in recent months. And then I'm going to talk briefly in a fairly sketchy manner about future projects and open problems that I think are interesting. So let's start with designing for analyzability. And here, as a key example, we're going to look and focus in on the Rider app. So in 2016, Uber completely rebuilt its Rider apps from scratch, right? And apps is plural because we've got pretty separate code bases for iOS and Android. So this is a pretty ambitious task, and it was a success. And one of the key reasons was because of some new architectural designs that some of the core platform engineers put into use for these apps. And the key goals of these designs included high availability of core flows. And I'm going to talk in more detail in a couple slides, but core flows are sort of the most important features of the app. We want people to work on sort of less important features, but not have that work compromise the core functionality. And also maximal decoupling of features so people can work independently. And I'm going to argue that these goals will also help in the future static analyses that we build. So one of aspects of this architecture is a plugin architecture, which I think we're all familiar with. It's not a new concept, but it's quite cool how they actually pulled it off in this app. So plugins, a key functionality that they provide is that they isolate the core flows from other features. So here, a core flow in the Rider app would be actually booking and getting a ride, but a non-core feature would be something like changing your account settings, like your mailing address, right? That's not something that's absolutely crucial, we would say, compared to the core flow of booking rides. So plugins enable us to separate these things, and because of that, they de-risk feature experimentation. So any code that's inside a plugin, we can actually disable with a flag from our server if it's causing problems. So in the field, we're seeing a lot of crashes. We can turn off a plugin as needed. And if we look at the app, actually a lot of stuff that you see here is implemented via plugins. So we've got this feed at the bottom with extra information, location shortcuts, this button which takes you to scheduled rides, this button for features. All of these are plugins which, with the flip of a server-side flag, can be disabled individually. So under the hood, we have this notion of core code and optional code. And the core code defines where the plugin points are, and these are essentially arbitrary plugin types, but it's all done via Java generics. You might be familiar with other plugin systems that use XML files and reflection to write plugins, and thankfully, from an analysis perspective, none of that is there here. So any change to the core code gets additional review from a set of the people who designed sort of the core application, and to double check that this is critical code that can't be turned off, right? So it needs additional review. And then there are linting rules that assure, even at build time, that the only way core code can reference the non-core code is via this plugin system. And one interesting thing is that, so 80% of the code in the Rider app is actually sitting in plugins, which I think is quite a success. You could have imagined that, this design wasn't flexible enough and everything starts leaking into the core, but it seems that that didn't happen. And there are automated UI tests where essentially all the plugins get disabled, and on every commit, these UI tests ensure that the core flows still work. Okay? So that's one cool aspect of the architecture. Another one that I found quite interesting was this notion of Deepscope Hierarchies. And this is dealing with a very tricky problem in mobile applications, which is trying to scope the application state and manage lifetimes of this state. So it's clear in a mobile app that some of your state needs to be shared between different features. So maybe the most obvious example for the Uber app is the map, right? A lot of different features need to know about the map and the location, But there's also other things like the user account information. Once you're actually logged in, a lot of different features are going to have to know different information from your account, like payment methods and such things. Now, key question is, where do you keep this state? And this kind of goes back to the keynote in some sense, that global state is the bad solution to this problem, right? For any number of reasons. I probably don't need to tell this audience about this, but data races, subtle dependencies creep in between features. This is a bad idea. Another crucial aspect of this for mobile applications is that we really need to manage the lifetime of the state very carefully to avoid leaks. So a lot of mobile apps, you kind of open them, use them for a bit, and then you hop right out. But if you think about our driver app, for example, that might be just the only app open for hours, right? And so if we're leaking state, it's going to constantly be crashing without a memory error exceptions, which is a really bad experience for drivers, right? So more specifically, say after you take a trip for the driver app, you really want to guarantee that all the state and objects associated with that trip are discarded, which can mean different things on different platforms. Like on Android, it means they're garbage collected. Maybe on iOS, it means that everything is freed. And in the old Writer app, there were a lot of different conventions around this, trying to null out pointers, or in some cases, you try to reuse objects by writing these reset methods to unset the state. But it was all quite fragile, and there were just a lot of leaks. So in the new app, they've added this notion of Deepscope hierarchies, which are kind of like region-based memory management. That's how I like to think of it. Let me illustrate it with an example. So you have these scopes, which are dynamic notions in your app. So you start out with a root scope, and we really try our best to have very little state stored in this root scope, because this is essentially global state. But then you introduce new scope as your app transitions into different phases. So initially, you might have this child scope, which is logged out, right? So this will have all the state necessary to enter in your account information and password to log in. And then once you're logged in, a new scope is introduced for this logged in state, and then the logged out scope kind of disappears, hopefully with all the state and objects corresponding to being logged out. So similarly, now that you're logged in, you might enter a request scope, all the state needed to make a ride request. And then once you make that request and you get in the car, you're on the trip. And hopefully all this request state can just be cleaned up and goes away. So they have strong conventions around this scope tree. So we have parents, which create and destroy child scopes. And state must be explicitly shared from parent to child. You can see it in the code base that you have to pass this down explicitly. And you're actually statically prohibited from accessing any state from your siblings. So again, this helps to keep features independent here. And object lifetimes, if this is all done directly, is tied to the scopes. So once you kind of release a scope, all the corresponding state should be released also, which helps a lot with preventing leaks. This is all based on a new mobile application framework called the RIB framework that was defined at Uber, and we've talked about some publicly. Details aren't super important for the purposes of this talk, other than you can think of it as a refinement of model view controller with specific types of objects for managing the state sharing and tree structure. So what are the implications of all this design for program analysis? Well, the decoupling is really great for helping developers move fast, right? As I said before, with these scope trees and plugins, features, it's very easy to keep features independent, right? And this is actually a challenge with the amount of app state that needs to be shared. You have well-defined contracts, right? Like between features. Via this tree, you know exactly what state is getting passed in, what you're passing to your children. And also between the core and optional code via these plugin points. So this helps developers stay sane and not constantly get blocked by code that's irrelevant to them. I would argue that there's a potential for this to be really good for analysis also, for static analysis in particular. So one thing is that just because the app is designed this way, I think that whole program analysis will see some benefits, just because there are various kinds of data flows that are already explicitly prohibited. And so the app, when you do a whole program analysis, hopefully you'll get less pollution from imprecise data flow. But another really cool thing we could hope to do is more modular verification. So you can try to verify some strong properties of the core code, and if you know that plugins only behave in a certain way, you don't have to analyze those plugins. And similarly, of these individual features, if you know how they're interacting with other features via these deep scopes, again, you can try to do some modular verification. And this, of course, is going to require specifications at all these boundaries, okay? Which I think it's an open question how to get them. I would hope we can infer a lot of them, but this is going to require some digging for each individual analysis. But I think this is really quite a big opportunity because we've got a huge code base here. You know, as Avik said, you know, you can't scale whole program analyses and actually get the performance that you want to need, that you're going to need. But leveraging the app design, I think, could really lead to huge performance and precision improvements. Okay, so now let me switch gears, kind of, to talk a little bit about the Novice checking that's done in our Android app, which does sort of take into account some of the higher level principles that I talked about before in terms of try to do things modularly and scalably. So I've identified some of the principles for bug checkers that seem to work well in the Uber mobile application development so far. So one is we really want to block the build, okay? So if your checker is reporting errors, you shouldn't be able to merge your code back to master. We want to keep master green. And what's the reason for this? People are trying to move fast, they're focused on their features. If you print out a bunch of warnings and say, take a look at these might be, you know, a problem, they're going to say, this is just noise. I'm not looking at this. I just got to get my code committed, right? So we really want this to block the build, but this means precision is critical. False positives are just going to, you know, cause a lot of problems. We also want to run checks as early as possible. So we have a fairly standard development pipeline, which I'm not going to get into detail, but basically you develop locally, and then when you have a change, it goes through code review, and we run lots of tests in our continuous integration system. And then eventually, before you merge back your code, there might be even more tests run. So you can think of these as stages in a pipeline, and we'd really like to run our checkers as early as possible. We'd like to aim even for instant feedback in the IDE. So performance is really critical. And finally, and again, this is in contrast to some of my previous program analysis experience, annotations are okay. If we can only incur a modest annotation burden, and we can really make the analysis work better, the development teams are very open to sort of requiring annotations if the properties we're trying to prove are very important. And so this leads into how we do null pointer checking in our Android app, which is sort of a type-based approach, which I'll illustrate briefly with an example. So let's say we have this logging function that's just taking an object and printing out its string representation, but here we're calling it with null. So in our type-based approach to checking, you're first going to get an error here because we assume that any parameter or return type or field is not null unless it's explicitly annotated otherwise. So here you get an error. You can't pass null to this parameter because it's supposed to be non-null. You can try to fix this by adding this nullable annotation here, but now you'll get another error saying, hey, you're dereferencing something nullable, so that's going to cause potentially a null pointer exception. And finally, you can fix this by adding a null check, which the type checker is smart enough to reason about and says, okay, now this code is fine. And this is done in a few previous tools, such as Eradicate, which is a part of Facebook's Infer tool, but also previously in the checker framework, and I think even going back to tools like ESC Java. So what's our experience been with doing this kind of checking? So this was deployed aggressively in 2016 using the Eradicate tool across Uber's Android code base, and it had a huge effect, just a huge reduction in null pointer crashes in the field when they did this. Now, there was a very significant initial annotation effort because we had to add nullable annotations for everything that could legitimately be null, and they did it. I wasn't around for that. I kind of feel bad for them, but they pushed it through. They saw it was worth it, and they saw a huge reduction in crashes. The downside here was for how we ran this tool, the Eradicate tool, the performance was not quite where we wanted it. So we wanted to keep our master green, which meant 0 warnings. But with the performance of this tool, we actually couldn't reasonably run it on developer laptops. I mean, they could run it, but it would take on the order of minutes, and no one would. So the only time we would enforce these checks is very late in our CI pipeline. And that's not a great experience for developers, right? You have your new code feature, it's gone through code review, almost all the tests have passed, and then a couple hours later you get a null pointer warning. It kind of breaks their flow if they've been moving on to something new. So as a solution, recently we re-implemented this kind of check-in as a plugin to this tool called ErrorProne. It's an open source tool from Google that essentially lets you write your checkers as plugins to the Java compiler. And this is great for performance because we can reuse all the work that the Java compiler has already done in terms of building an AST, in terms of type checking. We can just reuse that pre-computed work. And as a result, now we can do this kind of checking and give very quick feedback on local builds. So we've got, as I've measured it, 5 to 10% overhead. It's quite manageable. And now developers, every time they compile, they get these kind of null pointer warnings. So people are really happy with that. And now Avik talked about soundness, and I've got my soundness slide too. So how sound is our checker? It's not sound. And I would say it's not even soundy, in that we have there are all kinds of constructs where it's actually well known how to handle them soundly, but we make a deliberate choice not to because it increases the annotation burden or forces you to rewrite certain code patterns, and we haven't seen corresponding benefit in terms of a reduction in actual crashes that are happening in our app. Right? And I'd say this is a good point of contrast with, say, the null pointer checking that's available in the checker framework, which is trying much harder to catch every little loophole that could lead to a null pointer exception. So, I mean, I can't even list all the holes, but multi-threading, arrays, mutation, there's all kinds of ways our tool is unsound. What I do, though, is I keep an eye on what null pointer crashes are actually happening in production, and is it something that we could easily address in our tool. And a lot of them are actually deep in the guts of third-party libraries. So there's very little we can do about that. But once in a while, what we could do is improve our modeling of these library methods so that we would actually check where our code is calling into the library that you're not passing null, or null is not in a certain field. And there are some good ideas about there how to even infer these library models that we might be looking at in the future. One other interesting question is, you've got these annotations in your code about nullability. But what about data that's coming in over the network or from disk and then getting marshaled into data structures? How do you know that that is well formed, right? You might assume that some field is always non-null in a network response, but you might get invalid data coming in over the network, and then all your assumptions go out the window if you actually get a null value there. So at Uber, they wrote this tool called Rave, which is open source, which actually turns your nullability annotations into runtime checks at this border between your code and the disk and network. So at the border where data is coming in, we use Rave to make sure that whatever nullability annotations were written statically actually are adhered to at runtime, and we have some extra checks and other code pads if you have invalid data. So there's a bunch of open challenges. One, to make this checker better, one that I think is pretty fun is around streams, which is used heavily in our code base. I'll talk about more later. But here's a simple code example. So let's say you've got a data class that has a bunch of data about like age and other things. And then we've got a person who has a data function, but it's possibly null. Okay? So there may be no data associated with that person. So now let's say we have a stream of these person objects, and first we filter such that we only keep the person objects with non-null data, and then we do a map operation, like we're trying to sum all their ages, right? Just looking at this code, we filtered out all the person objects with null data, so it's safe. But our type-based null checker doesn't know this, right? It's going to say here that you might be dereferencing a null data object. So I think it'd be very interesting to work on type system extensions to try to be able to understand these stream constructs better, understand that filter imposes additional predicates on the remaining objects in the stream, and to use that to actually avoid reporting errors here. And this actually shows up a lot in our code base. It might be one of the, probably the biggest source of false positives with our checker is due to these streaming constructs. So I think it'd be quite cool to think about type system and type inference extensions to handle code like this. Okay, so in the last part of my talk, let me just talk briefly about some open problems that we're working on right now and that we'd like to address in the future. So one thing that I think is really quite promising is doing better analysis of experiment flags and how this affects your code base. So experiment flags enable us to remotely enable and disable features. And I kind of already talked about this with the plugin system, right? So we can use our experiment flag infrastructure to disable plugins. but it's also used for things like A/B testing of different features, and also to gradually roll out a new feature to play it safe, right? In case it's causing a problem, we don't instantly deploy it to millions of people. And in the code, it looks something as you would expect, right? You call into the experiments API, you say, if this new feature is enabled, let's run the new feature. Otherwise, let's run the old one. But it can get a lot more complicated than this, right? I'm not going to show it in the slide, but sometimes if this is enabled, we store some state in a field. And then in some other chunk of code, you read that field out and do some actions. And it's not immediately obvious, just staring at this code, what impact these flags are having. So one thing I've been working on is a static analysis to give greater visibility into how flags affect different parts of the code. So the thing that immediately came to mind when seeing this is, let's compute a forward slice to try to see how this flag affects different code. Now, when you're dealing with real-world Java code, things like the heap cause slicers to not scale very well. I've been using a technique that we used before for security analysis. We called it hybrid thin slicing to try to deal with the heap more efficiently. And one thing that I'm just starting to look in is how can we leverage that application structure that I showed you before to do a better job here. We've got these scope hierarchies. We know the siblings can affect each other. So ideally, we should be able to cut off slices that we just know can't cut across these sibling features. So that's something I'm still thinking about and trying to work into this analysis in a clean way. And I think once we have it, there are going to be many use cases for it. There's lots of interesting questions you can answer. For example, you've got a crash in the field. What's the best flag to turn off to stop this crash from happening? It'd be great to be able to answer that with the analysis. Or someone is trying to push a change into the app, and we think it's kind of risky. Already, we actually require developers to say, what's the revert plan on this change? What flag can you flip in order to turn this off if it doesn't go the way you expect? But there's no analysis that's actually checking that all those changes are gated by the stated flag. So if we could check that statically on the diffs, I think that could be quite valuable also. And there's a bunch of other applications of this, so I'm pretty excited about what we could do with this. Another aspect of reliability that we're working on is multithreading, which, as we all know, can cause all kinds of nasty bugs, right? Data races are the classic example. In mobile apps, another thing that we worry about is that certain tasks need to be performed on certain threads, or more particularly not on certain threads, right? At least on Android, and I think also on iOS, if you try to touch any of the UI data structures and you're not on the main thread, then your app is going to crash, or worse, it's just undefined behavior, and it's going to do something weird way later on. An interesting thing about the mobile app code at Uber is that almost all the multi-threading is done via this framework called ReactiveX. It's a framework for doing functional reactive programming for asynchronous streams, and it gives you a nice abstraction for dealing with things like network requests, user clicks that sort of come in asynchronously, and you want to sort of process them as they come in and specify the operations in a more kind of declarative manner. But what's interesting is this framework implies a very structured use of multi-threading. So here's an example. So the streams are called observables in ReactiveX. So let's say we have some source values, a source of observables, and let's say you want to do some expensive computation on these values. Well, you call this function observe on, and you pass it this marker that says put it on some computation thread, and this means everything after that is going to happen on a computation thread, right? So now we can do this expensive computation, something like a map operation, but now we need to render the results to the UI. And in order to ensure that that happens back on the main thread, you add another observe on call and say, okay, now let's run the subsequent operations on the main thread, and then at the end, you can display your results. This is essentially how the multi-threading code works in the apps. There's very little use of explicit thread creation or executors or anything like that. So I think this is quite an opportunity for building specialized analyses that understand this reactive paradigm to doing multi-threading, and then can do a really good job of finding multi-threading errors. So one interesting thing is that a lot of these operations, like these maps and filters, really they're supposed to be side effect free. So I think if we could actually show that they're not side affecting any global state, that takes us a long way towards dealing with race conditions in the app. And then if we can keep track, you can see that even in a type-based manner, you might be able to keep track of the thread that's associated with one of these streams. If we can track that with analysis, we can get a handle on, say, ensuring that when you're displaying a result, that the corresponding stream is already back on the main thread. So I think there's a big opportunity to really just get a handle on almost all the multi-threading issues in our apps by specializing it to this Rx structure. So one last thing I'm going to talk about, what's a really big issue for us, is performance, both execution speed and memory. So this is a Micromax Spark. It's a phone that's quite popular in India. The Micromax is an Indian brand. This is about, I checked recently, about $60 to buy one of these phones. So one of the things is it's not very high-end hardware, both in terms of CPU, but also in terms of memory and flash speed. But it's really important for the Uber app to be able to run smoothly on all devices, particularly these low-end devices in markets where there's a lot of growth, like India, like Latin America. And here, honestly, it's kind of wide open, and if anyone here has answers, come talk to me. There's a lot of different things we could try to do. We can try to statically detect if there's slow code running on the main thread, maybe using things like what I talked about on the previous slide, try to give visibility into which network requests have results that are blocking the UI, try to analyze things to reduce out-of-memory errors or memory leaks, and try to leverage that app infrastructure I talk about. But here the real challenge is new features are going in constantly into the app, right? And we really, again, need to be precise and scalable in our tooling. So I don't know off the top of my head of analyses, like particularly static analyses, that we can plug right in here to get a huge win. Maybe dynamic analysis is a better approach. This is something we're going to be thinking about a lot, though, because it's really important. So that was just a couple examples, but there's a lot more stuff that we're thinking about. Analysis of Swift on iOS is a huge open problem for us. We're investing a lot on the app development side and writing Swift code, but we need to build up some infrastructure for doing static and dynamic analysis there. There's certain startup code that is sort of very critical to the app. So if we have a crash there, you might end up in this crash loop where you can never actually start the app. So I think that might merit stronger verification to ensure that we don't end up in those crash loops. Lots of code duplication across our apps. It's an interesting question. What can we do about that? Regression test selection, I think, could help a lot in terms of speeding up the jobs that we run in our contiguous integration structure. I mean, there's tons of problems to work on, and a lot of opportunity for impact, I think. So this is what really excites me. So that's all I had. In conclusion, I think analysis has a really great chance to help kind of square the circle at Uber in terms of achieving high app reliability while also enabling developers to move fast and work independently. And the way that we're going to aim to do this is by modularity, both in the app design and in the analyses that we develop, and have the two kind of feed off each other in kind of a virtuous circle. So thanks. There's an Uber engineering blog where you can read about some app specs of our app architecture. So if you go to eng.uber.com, you can read some more details about these things. And thanks, I'm happy to answer any questions.
So we have some time for questions. If you'd like to ask a question, I will direct you to the center mic.
Hello. First of all, awesome talk. Good question. You mentioned that so many devices out there and it's a problem. So how do you actually measure their performance? Like whenever you, let's say, start A/B testing a new feature, do you like monitor on what device it's running, how it's performing, and so?
Yeah, it's a good question. I mentioned the experiment flag infrastructure, and that gives us the ability to only deploy certain features to, say, certain geographies also. So that can help us keep track of where things are running. In terms of actually measuring performance, we have some infrastructure based on code instrumentation in order to selectively sample and measure these kind of things. But it's a tricky problem because that doesn't give you complete visibility into low-level things like native code. Sometimes you have app freezes, which are due to blocking a thread, right? So that's not going to show up as much in execution time. So we have some handle on things like startup time and how much time individual functions are taking, but I think there's more work to be done there in terms of getting really, really good information from the field on the performance implications of these different features.
That's it. Thank you.
Hi, I was wondering if you're going to open source your new version of Eradicate.
Yeah, absolutely. It's in the plans, so I know hopefully within the next few months we'll have some good news.
Awesome.
I'm working on it.
So I was wondering, so you said you have these quick soundness checks to make the developers develop quickly, but they're not very soundy even, right?
Yeah, specifically with the nullness checker, yeah, there are various unsound aspects of the checker.
Right, but on the other hand, you said you had this checker that actually gives very good results, very precise, but it's too slow.
So we were using a checker that was giving very good results, but didn't quite have the performance that we needed.
But would it be a possibility, I mean, you can have the non-soundy checker for the developers while they're developing, but kind of in the evenings or in the nights that you run it with the more complicated checker, or is that something you already do?
That's actually, it's not something we do. It's a good idea to sort of have different features enabled in the checker at different stages of the pipeline, and maybe on a nightly basis do more rigorous checking. It's something that we're thinking about, but isn't deployed yet, but I think definitely something that we're going to have to do moving forward as we do deeper analyses, which no matter how much we optimize, just doesn't make sense to run on every single local build. So yeah, that's a really good point, and it's something we're looking at.
So I have another question which is completely unrelated. So you said at the end you had performance problems with some of these low-end smartphones, right? But your system's already set up that you can kind of disable features. Is that a way of kind of, for the user to kind of scale down his Uber application so that it actually runs performantly on his machine?
Yeah, it's a good idea. It gets kind of complicated for a couple of reasons. So firstly, that's a dynamic way to turn off a feature.
Yeah.
But one of the issues we actually have with low devices, even at installation time, just the size of the app can be quite big. And being able to dynamically turn off a feature doesn't turn off the size of the app on disk. So we need sort of an end-to-end solution for some of these things. And then, I mean, there's the general question of, well, which features should we disable? Should it be your feature or my feature, right? We've got all these different teams that care a lot about the features that they're delivering in the app. So,
but maybe the user says, I don't care about this feature.
Yeah, it's something we should think about more. I'm not sure that inexperienced users will be able to sort of, I mean, power users, absolutely, they'll love us for it, but I'm not sure that for our broader user base, they'll be able to find the right settings. They'll probably just stop using our app rather than going through that trouble. So, but it's a good point. We should maybe find ways to automatically disable features that are not performant and not critical.
Thanks.
Okay, let's thank the speaker again.